Okay guys, so today we're going to look at one of our homologous series. We're going to have a look at the alkanes. I strongly suggest you go through the video first, then pause it, use bits as you work through the worksheets before you upload them to me. So, alkanes, what does this link into our last lesson? Remember, our alkanes are one of our hydrocarbons. They're part of the family of hydrocarbons. And hopefully you can remember from last lesson the really important phrase about what the hydrocarbons contain. And I'm hoping you're all going, only, that key word, only hydrogen and carbon. So our alkanes are made entirely of hydrogen and carbon. So we have two slightly different molecules here. The one on the left is an alkane. The one on the right is our other hydrocarbon family we had to worry about, the alkenes. So today we're going to focus on the alkanes, but to give you a little bit of comparison, alkenes is coming next lesson. What can you tell that's slightly different between the two? Well, the alkane has only single covalent bonds, only single lines between the carbon and hydrogen, whereas the alkene has the double bond between the carbons, the carbon-carbon double bond. We have phrases for this. We call alkanes saturated and alkenes unsaturated. By this saturated, we mean everything has a single bond. All of the atoms have single bonds between them. Whereas the unsaturated molecule, the alkene, has that carbon-carbon double bond. So a definition of these saturated hydrocarbons contain only, is that key word, only again, only single bonds. An unsaturated hydrocarbon contains a carbon-carbon double bond. Remember, we can't have carbon-hydrogen double bond because hydrogens can only make one bond, guys. Okay, so our alkanes are our saturated, our alkenes are our unsaturated molecules. So, to move my little camera a bit so you can see the end of the sentence. The alkane general formula. So you remember when we talked about homologous series, we said they all had to have the same general formula. So what we mean by this is that if you take the number of carbons, our number of carbons, which is our little n here, and you times it by 2 and add 2, that will give you the number of hydrogens on the alkane. So it should fit this formula. So if you think back to our molecules the other day, we had C2H6. Sadly, we don't get subscript on Zoom. So C2H6 was our ethane. It was an alkane. And it fits this formula because if you take the 2 carbons, times it by 2, 4, add 2, you get the 6 hydrogens. So an ethane, C2H6, is an alkane because it fits this general formula. Whereas if we had C3H6, which is one of our other examples, it does not fit this general formula. So we know just from the molecular formula that it is not an alkane. Okay, because it should be C3H8 if it was an alkane, because 3 times 2 plus 2 would be 8. So anything that fits, its molecular formula fits this general formula, then you are able to, what's the word I'm looking for? You are able to identify it as an alkane. So, a couple of examples, we've talked about these already. Methane, meth 1 carbon, ane alkane. Molecular and structural formula are the same in this case because there is only 1 carbon block. So our structural formula and molecular formula both say CH4. Our full display formula would be like this. Each has a single bond because we're an alkane. And then our ethane, 2 carbons, C2H6 is our molecular formula. Our structural formula would be CH3, CH3, because we've got to break it into the carbon blocks. And we have our displayed formula. You should be able to pause the video at this moment and do the empirical formula for both of them for me. So you should have found the empirical formula is different. The empirical formula for methane is the same as the molecular formula and the structural formula. CH4 is the simplest ratio that methane can be, whereas ethane, the simplest ratio it can be is CH3. That would be our empirical formula. So ethane has a different molecular formula, structural formula, and empirical formula. For methane, they're all the same. So now is your chance. You can go and name the rest of the series. So you have a worksheet attached on your Firefly. And meth, eth, prop, but, pent, hex, hept, oct, non, dec tell you how many carbons you have. So if you have a molecule with 8 carbons, you would call it oct something. And you should now be able to fill in the molecular formula, the structural formula, displayed formula, and name the chemicals, because all of our alkanes are in the ane family, so they would all end in ane. So pause your video, go away, complete that sheet, upload it for me. Okay, a few other little points about the alkanes. Another thing about homologous series is they have physical trends, so that they show a pattern. If you change the size of the family, you get a pattern in the trends. There are 2 main ones you need to know about. The first one is the melting and boiling point trend, which is as the alkane becomes larger, the melting and boiling point becomes higher. And we will answer this why in a second. And the second one you need to know is about the color. So as the alkane becomes larger, the color becomes darker. So methane, our 1 carbon compound, is a colorless gas. Decane, our 10 carbon compound, 10 carbon alkane, is a dark yellow liquid. And bitumen, which is 80-ish carbons long in that region, is a dark black tarry kind of color. You don't need to know why the color changes, but you need to be able to identify the pattern that it gets darker as the alkane gets longer. So now, why does the melting point and boiling point get higher? So why? It all comes back to our structures topic, guys, and so we talk about you've got to revise all the topics. And it all relates to those weak forces between your simple covalent molecules. So alkanes, guys, are simple covalent molecules because we can draw our covalent bonding diagrams. You can do the overlap. You did draw them when you did bonding back in year 9. So going back to our structures topic, the bigger the molecule is, the stronger these weak forces can be. So if you imagine you have a very small molecule, it hasn't got a very big surface to interact with another very small molecule. Okay, so when they reach one another, there's not much interaction going on. So it's quite a weak force. Whereas if you have a big, long molecule, like a decane, there's lots of surface that they can touch on and lots of interaction, so the force will be stronger because there's more surface that they can interact with. So as the forces get stronger, you need more energy to pull the molecules apart, which means the melting point and the boiling point will go upwards. So hopefully we now have enough details to do all of the worksheets that I've set you. A few little pointers that you might want to make a note of. You need to remember those prefixes, the 1 carbon meth, 2 carbon eth, 3 carbon prop. I strongly suggest you write yourself a mnemonic or something like that, like monkeys eat peanut butter, etc., etc. Remember with your displayed formulas, capital C's and capital H's. Like on the periodic table, carbon is a capital C, hydrogen is a capital H, so don't use lowercase. Remember that the little dash, the line in between, is a covalent bond. 1 dash means 2 electrons, 2 dashes means 4 electrons, 3 dashes means 6 electrons. And remember the numbers in the formulae are in the floor and not in the sky, so it's CH subscript 4, not CH superscript 4. Hopefully you should be able to get through all the worksheets now. I will be on Teams to help you, so upload your work. Have a good day, guys.